Considering this is an introduction to MATLAB course, I think it's safe to assume that I went overboard with this final project. Just a little bit. I'll get into why I went overboard later, but let me just show you how much work I put into this project. What you're looking at is my entire MATLAB program in one file. It's over 1,100 lines of code, 31 user-defined functions, and over 100 hours of work. But what exactly does my program do? In short, my program can calculate the trajectory of any object relative to Earth's surface. This includes, but not limited to, trajectories of falling objects, re-entry trajectories, orbits, and missiles. Furthermore, all objects can interact with a dynamic atmosphere with a changing pressure, density, and temperature as a function of height, and can even get this data from real life using NOAA's website. When you get the data from NOAA, it even picks up the wind data, so the wind can interact with the object as it flies through the air. So without further ado, let me show you my program. So here we have the main script of my program, and as you can see, it is a lot of comments and not a lot of code. In fact, there's only 3 lines of code in this entire script. And the reason for this is because any program can be broken down into 3 parts, that being input, computation, and output. And so for this project, I want to emphasize that, so there's only 3 lines of code in the main script: the GUI input, run simulation, and plot output. So technically speaking, the entire program is only 3 lines of code, at least in the main script. So let's go check out the GUI input and see how the GUI input works. So the GUI interface is actually broken down into 4 main sections, that being object parameters, environmental parameters, starting condition, and simulation settings. So let's start with the object parameters first. So in the object parameters, we have the mass, volume, area, and drag coefficient. Now you can change these values on your own, or you could select this little drop-down menu and you can click bowling ball as an example, and click the update button, and it'll automatically update the text so that it matches the parameters of a bowling ball, which is pretty cool. You can also have a static drag coefficient or have the drag coefficient change as a function of Mach number. Similarly, you can have a thrust curve, so if you want to launch a rocket, it'll get the thrust data from a spreadsheet. You can also randomize the values, but for now we'll just keep it as a bowling ball. For environmental parameters, there's 3 main options. There's a static atmosphere, a standard atmosphere, and an atmosphere based on location. Now, the location is pretty interesting because it gets the data from real life using NOAA. In this case, it'll get it from Jacksonville, Florida. And you can get these 3-letter identifiers on NOAA's website. And then, of course, there's also a rotating Earth and then a static gravity. In this case, it'll get the gravity as a function of height. Moving on to starting condition, there's this little globe, which is pretty cool. This red marker indicates the starting point. In this case, you can actually see it's above the Earth. It's pretty high up. So we can actually change this. Let's just say it's 30 degrees latitude instead of 40, update it, and it'll change the position of this little red dot. Here is the velocity vector. So you can change the direction of the initial velocity and angle relative to the normal. In this case, it'll be 30 degrees, so that's north-northeast, which is sort of this way, and 30 degrees in angle, and 500 meters per second launch velocity. Moving on to simulation settings, there is a delta time and delta time in space. Now, my program uses Euler's method, which means it takes tiny time steps to calculate physics. So given acceleration, you can find velocity and then position, and it uses that using a tiny time step. The smaller the time step, the more accurate, however, the more compute time and memory it'll take up. So to remedy this, there's a maximum number of iterations the computer can run, as well as a max compute time. And this is to prevent the memory from overloading or your computer from running for a long time. So it'll only run 250,000 iterations, and it'll only run for a maximum of 4 seconds, or 5, you can change it. Now the only thing left to do is to actually launch it. So when we click this big red button, it'll launch it and plot this figure. Now it shows information about the flight in these 6 plots right here, as well as it shows atmospheric data on this plot over on the right. So it shows the changing in temperature and density as a function of height, as well as relative humidity. On the bottom left, there is the total time, the number of iterations, max height, just text information about the flight on the bottom left. Next to that, there's options for the 3D simulation. So there's the frames per second of the simulation, as well as the number of iterations per frame. So if we only want 1 iteration per frame, it'll take about 100 seconds, but if we only want 6 iterations per frame, it'll take about 17 seconds to run. Now, it's one thing to look at the graphs, however, it's a completely other thing to actually watch it fly through the air. What you just saw was a 3D simulation of the projectile launched at 720 kilometers and 5,000 meters per second. In this particular case, it was suborbital, but with a few modifications, you can simulate ballistic trajectories, re-entry trajectories, orbits, and missiles. With well over 1,000 lines of code, it's going to be impossible to go over everything. However, I think it's important to go over how it actually calculates the trajectory. And that happens in this while loop right here. It's about 40 lines of code. However, the most important part of this while loop is these 4 lines right here. And so, believe it or not, the entire program revolves around F equals ma. You simply solve for a, and you get the acceleration is equal to force divided by the mass. And if we look in our code, we get the acceleration is equal to the force divided by the mass. And from acceleration, you can get velocity, and from velocity, you can get position. Now, it is a little bit more complex, like you're all dealing with vectors, and you do have to get the sum of forces, which does take more computation. And there's obviously spherical coordinates and having the earth rotate, which adds complexity. However, the base program is simply F equals ma, which I think is very cool. If you're interested in spherical coordinates, there's a great PDF that helped me figure it out. I'll put it on screen as well as link it in the description. If you want to download my code, there's a link in the description to my GitHub. You can download it and run it for yourself. And so that wraps everything up. But there's still one more thing left to talk about, and that is why. Why did I spend so much time and effort into a program when I didn't have to? I didn't have to have 26 different options for the GUI interface. I didn't have to simulate the projectile in 3-dimensional space, and I didn't have to make this video, but I did anyway. And the reason is because I want to make something that I'm really proud of and see what I'm capable of. Because at least for me, I wanted to score for intellect rather than points. So the next time you're assigned a project, it might be worth it to go a little overboard to make something you're really proud of.